So we've covered a little bit of oxidation reduction already in chapter 7. But one definition of oxidation is that it's the gaining of oxygen. So if you're adding oxygen atoms to anything, iron, steel, rusting is probably the most immediate form of oxidation that you've seen, right? Making rust, a very slow oxidation process, but you're adding oxygen atoms to the iron and making iron oxide, which has different properties from iron itself. But you can also have rapid oxidation, like a flame, right? So to again touch back on chapter 7, a combustion reaction is a type of oxidation reduction reaction. So that's a rapid form of oxidation reduction reaction. So you're adding oxygen to carbon and getting CO2 and water, and those are always the products of a combustion reaction. But redox reactions don't have to involve oxygen, and it's weird, this is like cutting off the top. Redox reactions don't have to involve oxygen because the definition is just a loss or gaining of electrons. So here we can have lithium reacting with oxygen, right? That's a redox reaction. Here, lithium reacting with chlorine, not involving oxygen, also an oxidation reduction reaction. And from now on, I'm going to say redox because it's way faster. So oxidation is a loss of electrons. Reduction is a gain of electrons. And I think I have on the next slide the mnemonic for remembering those. So oxidation and reduction have to occur together because to gain electrons, they have to come from somewhere, and to lose electrons, they have to go somewhere else. So these always occur in conjunction or together. So if we're reacting hydrogen with water, hydrogen is oxidized, and it loses electrons. Actually, we didn't get the, oh, it's on the next slide, okay. So hydrogen is oxidized, making it the reducing agent. So this is a new term that we didn't have in chapter 7. The reducing agent causes the reduction of another substance. So these are always occurring together. So hydrogen, we'll go over this again too. Here it has 0 charge, oxygen has 0 charge. We'll also talk about oxidation states today. But for now, you can think of this as charge. And then over here, it actually has a 1 plus, and oxygen is a 2 minus. So to go from a 0 charge to a positive charge, it has to lose 1 electron. That looks like I wrote an H, but that's a plus. So it loses 1 electron to oxygen and gives it this 1 plus charge. So hydrogen is oxidized, and that makes it the reducing agent. So these are very confusing because it's like a flipping of the terms. Always identify what's being oxidized and what's being reduced first. Then, whatever is being oxidized is the reducing agent because it's giving those electrons away to, losing those electrons to the other agent in the solution. And then the whatever is being reduced is the oxidizing agent, because reduction is gain, so it's gaining electrons from the other one. So the transfer of electrons.
So whatever is being oxidized is the reducing agent, and whatever is the reducing agent is being oxidized?
Whatever is being reduced is the oxidizing agent. So agent means it's making something else be oxidized or reduced. So yeah, oxidizing agent is the oxygen in this case, oxidation of another substance. So the mnemonic for remembering oxidation and reduction is oil rig. There are some other ones if you don't like those. I like oil rig because it's very concise. There's no extra words there. Oxidation is loss, reduction is gain, right? Oil rig. And in both, talking about transferring electrons. So always do, we could do that better. So identify these first. And you're oxidizing, whatever's being oxidized or being reduced is always going to be in the reactants. Because every chemical reaction, when we're writing it out, is a process. And so we're talking about this, the reactant. Did it lose electrons or did it gain electrons going from the left side to the right side? Some examples then. So identify the substance being oxidized and the substance being reduced in each reaction. So the sort of general procedure for these is, at least as we have it now, is we can identify charges of things. So we'll use the charges to identify whether or not they're gaining or losing electrons. We talked about last week for molecular compounds, that doesn't work because they don't really have charges. But we'll get to that. But for now, looking at this potassium and chlorine reacting, what charge do potassium and chlorine have in the reactants here? I'll give you a hint, it's the same. Potassium will form a +1 charge. So whenever we have anything in a reaction is by itself and doesn't have a charge written, its charge is 0. So we don't write the charges, we don't write these zeros in, but they're there. You can zoom this in. The reason over here that we don't write charges in is because they're written together, so they cancel each other's charges out. So now on the product side here, potassium has a +1 charge, or a 1+. And what charge would chlorine have here? Yeah, 1- charge. So which is the oxidizing agent? Or sorry, not oxidizing agent. Which one's being oxidized? Oxidation is loss. Which one's being reduced? Reduction is gain. What? Potassium is being oxidized, yes. So the hard part with this is, remember, we're moving around electrons, and every electron is a negative charge. So yeah, potassium is being oxidized. So chlorine is being reduced. Just to demonstrate this. So the reason that elements have charges is because they have different numbers of electrons than protons. Number of protons never changes. So if we look at just potassium real quickly, right, how many protons does potassium have? 19 protons. So I'm going to write this as a P+. And for neutral potassium, how many electrons does it have? 19. Yeah, it's the same. So for neutral potassium, protons and number of electrons are the same because protons have a +1 charge, and every electron has a 1- charge. So if you have the same number of each, you end up with 0. Right? So we can do this as 19 protons minus 19 electrons equals 0. So that's why potassium by itself, neutral potassium, has a 0 charge. But when we move over to this side, we have now potassium with a +1 charge. So potassium's still going to have 19 protons, but how many electrons does it have now? Heard somebody say it. 18 electrons. So it's lost 1 electron. Because now if we do 19 protons minus 18 electrons, we have +1. So just remember, if anything goes from, if anything's charge gets more positive, then its losing electrons. If it gets more negative, then it's gaining electrons. Okay. So what's the charge for B? What's the charge on aluminum? In this, as written right here. 0. So aluminum here has a 0 charge because, again, it's written by itself. It's not combined with another element, and there's no charge written, which is in direct contrast to tin. What's the charge on tin? Yeah, 2 plus. So there we have an element written by itself, but it's written with a charge, so we know what its charge is. So I don't need to write that one in. And then aluminum over here goes to a 3 plus, and the charge on tin is 0. So which is aluminum or tin being oxidized? Yeah, aluminum's being oxidized because it goes from 0 charge and it gets more positive. So that means it's losing 3 electrons. So this is being oxidized. Then what's being reduced? Tin. Because tin, well, each of the 3 tin atoms is gaining 2 electrons. So we have 2 aluminums that lose 3 electrons for a total of 6. 6 electrons lost, and then 3 tin atoms which each gain 2, so they're gaining 6 total. So balanced swap of electrons there.
Is it safe to say when you see a plus whatever it's reduced? You always see a plus?
Oh, if it starts on the left side with a plus?
Yeah. You always, would it be safe to say?
Not always, because it could go from a 2 plus to a 3 plus. So it'd be getting more positive. So it could still even lose an electron, even if it starts with a positive charge. So you can't say like always going to be that, and you're not always going to see the charges.
The more positive it gets, it's getting reduced. Electrons are getting reduced more, right?
Yeah, try not to think of as reducing the number of electrons as the same thing as being reduced here, because reduction is gaining electrons. Oxidation is losing electrons. Yeah. In that sense, it's backwards. We're going to talk about oxidation states, though. So how about for C, what is being oxidized and what's being reduced? This one's trickier. They both start as 0. And here we wouldn't even say that they're 0 charge, but there's 0 oxidation state. So, but then how do we tell what they are on this side? We haven't really talked about the tools that you would need to actually figure out which one is being oxidized and which one is being reduced, or what their oxidation states are in a molecular compound, because they're not bound together by swapping electrons, which is part of what we're going to cover today. The other thing to know, though, about redox reactions, oxidation reduction, is that oxygen, let's just say this, something reacting with oxygen is being oxidized, which is why it's called that. So here, carbon is reacting with oxygen, so carbon is being oxidized. We're adding oxygen to it. And the oxygen is reduced, is being reduced. Yeah.
So is it not normally the case that the cation is going to be the oxidized?
It is normally the case that yes, cations, if they're starting with a 0 charge, will generally be oxidized because they want to form positive charges. Anions in general will get more negative and become reduced. Yeah. Not always the case, though. Okay, this one's the exact same problems here as we had before, but now we're not looking for just what's being oxidized and what's being reduced, but the oxidizing agent and the reducing agent. So like I said, first identify what's being oxidized, what's being reduced. So what was being oxidized in this problem? In A? Potassium, yeah. So this is being oxidized, and then chlorine is being reduced, which is the oxidizing agent. Chlorine. Chlorine is the oxidizing agent, which makes potassium the reducing agent. So oxidizing agent, reducing agents are flipped from what's being oxidized and what's being reduced. I know it's a
So when it's being reduced, it's always oxidized. When it's oxidized, it'll be reduced.
agent. Yeah, specifically the agent on the end. This is why I say if you can identify first what's being oxidized and what's being reduced, then you flip it for the oxidizing agent, reducing agent. So just remember, oxidation is loss, reduction is gain. There's a lot of flipping on these. Okay. How about for this next one? Again, what's being oxidized? Aluminum. And then so, again, oxidation and reduction always have to occur together. So if we only have two things reacting, one of them we know is being oxidized, the other one has to be reduced. Wow, that's not how you spell that. And so now we flip it. So the oxidizing agent, or the oxidized species, is the reducing agent, and the reduced species is the oxidizing agent. How about for C? Is carbon being oxidized? Hands up if you think it's carbon. How about oxygen? Is oxygen being oxidized? There's a lot of indecision in the room.
Well, oxygen can't be oxidized because oxygen would be the oxidizing agent because it's oxygen, right?
Yes, oxygen. Yeah, if it's oxygen by itself, I think it's always the oxidizing agent. So carbon is being oxidized. And oxygen is being reduced, which makes oxygen the oxidizing agent, and carbon is the reducing agent. Yeah. So for problems like C, we need a way of identifying more than just like what their charges are, whether or not they're gaining or losing electrons, because it's not always going to be obvious, sometimes even less obvious than in that problem. So that's why we have oxidation states, which you can think of as electron bookkeeping. So if you're trying to determine what's being oxidized and what's being reduced, use oxidation states to keep track of the electrons and where they're going in chemical reactions. So all shared electrons are assigned to the most electronegative element. So electronegativity, oh yeah, we have periodic tables. Electronegativity is a property of the periodic table that we haven't gotten to yet. We're going to cover it in, I think, chapter 9. But farther right on the periodic table, more electronegative. Farther up on the periodic table, more electronegative. And for me, it helps to think of it like this. Fluorine is the most electronegative element. It sets the bar. There's nothing more electronegative than fluorine. So that's the most electronegative. The least electronegative is like francium at the bottom left. So going up and to the right, as you go from francium to fluorium, you're getting more electronegative, meaning they have a stronger attraction towards electrons. They pull all the electrons towards themselves. Okay, so the oxidation state or oxidation number is calculated or computed for each element based on the number of electrons assigned to it. And we'll get to that. But it's going to be the same in some situations as the ionic charge, so the charges that we've talked about with ionic compounds, but not always. So yeah, the easiest way to assign oxidation states is follow these rules. So this is where I was talking about the oxidation state of an atom in a free element is 0. So that's where if you have it written by itself in the chemical reaction and there's no charge assigned to it, then its charge is 0. Its oxidation state is also 0. The oxidation state for and this is where the ionic charge is the same as the oxidation state, for a monoatomic ion, so it's like the tin and aluminum problem that we had before, where it's just tin written by itself with a charge written on it, that's when the oxidation state and the charge are the same. So written by itself, given a charge. And the sum of the oxidation states of all the atoms depends on a couple things. If the molecule, so something like H2O, right, is written without a charge on it, the oxidation states will add up to 0, because technically its charge is 0. So for a neutral molecule, it's 0. And if you have an ion, so something like nitrate, NO3 minus, it's written with that charge, then the oxidation states all add up to -1. So the oxidation state, the sum of the oxidation states in an ion is equal to the charge of the ion. And then another place where the charge is the same as the oxidation state, which does happen, is in group 1 metals. So that's, right, group 1 is the first column. They all have an oxidation state of +1. Group 2 metals all have an oxidation state of +2. And then in their compounds, we assign nonmetals oxidation states according to the hierarchical table, which is on the next slide. I believe it's on the next slide. Where entries at the top have priority over the entries on the bottom. So here's that table of rules. So fluorine, I mentioned, is the most electronegative. So when we're trying to determine the oxidation states for a molecule or for any compound, you start with these. So fluorine is always going to be -1, unless it's by itself without a charge written. And then hydrogen's always going to be +2, oxygen's -2. Group 7, so the rest of group 7, which is where fluorine is, so chlorine, bromine, iodine, those are all going to be -1. 6A is -2, and 5A is -3 oxidation state. So I will give you this table. Again, kind of like the solubility rules for precipitation reactions. I'll give you the solubility rules table. It's your job to know how to use it. Okay. Examples are a must for these. So we have to assign oxidation states for each of these elements. So what would the oxidation state of A be? Assume these are written as part of a chemical reaction, right? For A, it's 0, right? So it's written by itself, and it's not given a charge explicitly. So it means its charge is 0. What about for B? Yeah. I guess I should write these like this, 2 plus. Actually, I'm going to do it like this. All right, so this is going to be 0. That one's 2 plus. How about for calcium chloride? Oh, yeah.
I have a question real quick. On the chart, did it have the charges before the limiters? or anything?
Oh, yes. The charges for oxidation states are different from, yeah,
The charge would go with kind of the numbers. Okay.
yes. So for calcium chloride,
-1 is the chloride.
yeah, so we have to assign it for each atom in the substance even. So for chloride, yeah, for chlorine, this is going to be -1. And it's -1 for each chloride atom. So each of those chlorines is -1. And then what is calcium going to be? There's +2. +2. So there's two ways that you can determine for the cation. So for the one that's going to have the positive oxidation state, I guess. One is to use, or at least in this case, right? Because calcium is in the second column, so it's going to have a 2 plus or +2. And chloride is -1. But the oxidation states here also have to add up to 0. And so there's no conflict in this one. But if we didn't know, I guess we're going to do more examples. This is going to take effect in this next one. Because what is the oxidation state for carbon? That's a bit of a trick question because we don't know what it is. It'll depend on what the anions are or what fluorine is. So what's fluorine's oxidation state? -1. And this is also similar to, well, it's very similar to charges where all the nonmetals are going to have negative oxidation states for the most part, and the metals will have positive. Carbon, though, so if each fluorine atom is -1, there's 4 of them. What does the oxidation state have to be for carbon then? +4. +4. Yeah, it has to be the opposite, yeah. Because carbon tetrafluoride here is written without an oxidation, or without a charge. So we have to account for that.
So whatever you come up with for this one, it would have to be for the carbon. because
Yeah.
it has to be.
Yes. Yes. Yes, and they have to add up to equal whatever the charge is on the molecule. So for nitrite, so NO2 minus, our two oxidations, or oxidation state for oxygen plus nitrogen is going to have to add up to -1. So what's the oxidation state for oxygen? 2 negative, or -2.
So nitrogen will have to be.
So there's, oh yes, yeah. Sorry. I was going to say, because there's 2 oxygens, so total of -4, +3 for nitrogen means that we have a total of -1. Because if we take +3 plus 2 times -2, then that's going to be -1. I'm writing out here specifically, yeah, oxygen, each oxygen atom has a -2. So that's how we think about these oxidation states. They're all going to have the same, for each atom, they're all going to have the same oxidation state. All right, what about sulfur trioxide? Yep, oxygen's still -2. So sulfur has to be, there's 3 oxygens. So sulfur has to be +6. Because if we have 3 times -2, right, that's going to be -6. So we have to add that to a +6 to equal 0 because there's no charge on the overall atom. I do want to point out for the nitrite, for E, right? So we have nitrogen and oxygen there. This is one where you technically need this table. because nitrogen is in group 5. So if there was no other element from the rest of this list, then it would be -3. But because we have oxygen, and oxygen's higher on the list, oxygen takes priority. So we do oxygen's oxidation state has to be -2, and then we determine everything else based on that.
So how do you know what it's a group that's in group 5? Where'd you get the group 5?
Oh, so, well, these periodic tables don't have it written like this. It's 5A. So 15 is 5A. So the A is talking about just main group elements, which is 1, 2, and then 13 through 18. So it goes 1A, 2A, and then 13 is 3A. 14 is 4A, 5A, 6A, 7A, 8A. I believe the periodic tables that I put on the exams they don't have group numbers at all, or at least that one doesn't.
Does it stop always at 7A or it goes to 8A?
It does, okay, so anything, yeah, so 8A is not on this. It's just not on this list.
Okay, but it does go.
Yeah. There is an 8A. Okay. Oh, right. So now you can come back to this problem and assign oxidation states for these. So carbon, element by itself is 0. Sulfur, also an element standing on its own, so that's also 0. And now sulfur is in which group? 6A. So it's going to have a, sulfur will be -2. So there's 2 sulfurs, so the oxidation state for carbon is +4. So now carbon, this is another way to think about these oxidation states. So oxidation is an increase in oxidation state, so meaning it gets more positive. So I know it seems like super basic to write out of the number line, but sometimes it just helps to have the visual of a number line. So I say more positive. This is 1 + 1, +2, +3, -1, -2, -3. So an increase in oxidation state means it's getting more positive. That's oxidation. A decrease in oxidation state is reduction. So if you have a hard time with keeping track of the electrons and how changing charges mean electrons are being gained or lost, try to just picture this number line in your head and say if we're moving to the right on the number line, that means it's being oxidized. If it's moving left on the number line, then it's being reduced.
So then the carbon's being oxidized?
So then the carbon's being oxidized because it goes from 0 to +4. And sulfur is being reduced because it goes from 0 to -2.
Wouldn't it be easier to do it that way? Like, find out, do this, and then if we go, okay, it's oxidized, because it's a +4, so that then we'll know it's reduced. When it comes to reduction and oxidation. You know
When
how
it-
you say you flip it?
Oh, for the agent.
Yeah.
Yeah, yeah. Yeah. Well, we didn't have oxidation states. When I explained oxidation loss reduction, it didn't have oxidation states yet. But yeah,
So we have it,
now that you have it, you can do this
this, and then flip it.
and then flip it. Yep. So if this method works better for you, use this method. If you can keep track of the oxygens and how those, or the electrons and how they change the charges, then do that. Either way works. Yeah. All right, so now we got not just identifying oxidation states in an individual element, we got a more complicated redox reaction here. We need to identify which element is being oxidized and the element that's being reduced. This is leading into how do we balance something like this. So this one's balanced. But we're going to talk about a half reaction method for balancing redox equations. And the first step is identifying what even needs to be balanced. So we can go through this and we'll do all of the oxidation states. So for tin, SN, what's the oxidation state? 0. Element by itself is 0. What about in nitric acid? Hydrogen's +1, and that is on the...
But it's not saying anything, so it would be 0?
Well, yeah, this is where things get a little bit trickier. So right, we have nitric acid here, and then we can use... Actually, can I just... let's see. Let's try this. Nope, come back. So we can use this table, while we're here. Hydrogen is really high up on this list. So it's basically always going to be +1, unless it's in some weird situation with fluorine, and then fluorine will override that. But basically, above all else, hydrogen has a +1, and oxygen has a -2. And so we're going to use those two facts to figure out what nitrogen is, because nitrogen's below both of those. Okay, so let's go back to that. Okay, paste this image. Make it smaller, put it over here. Okay, so we can come back to that. So hydrogen, we know, is going to be +1. And each of the oxygens is going to be -2. And so we can also write this. I'm going to write this as 3 times -2 to help us figure out what that charge on nitrogen has to be. So overall charge here is 0. So what are these ones that we know? What do those add up to? +5, -5, sorry, -5. So because this is 3 oxygens, and each of those has a -2, right? That's -6. +1 makes it -5. So the charge, or the oxidation state on nitrogen has to be +5. I'm going to write it underneath. Okay, so those are our 2 reactants. So for our products now, we have tin oxide. And again, we can look to oxygen first, because we know that tin on the periodic table is it's in 4A. So we don't know if that's going to have a specific thing, but we know oxygen's really high up on our hierarchy. So we start with oxygen, and that's going to be a -2. We can all do it like this, -2 times 2 of those. So tin is, yeah, +4. Remember, the reason these add up to 0 is because that molecule, that ionic compound, doesn't have a charge written for it. Okay. I've got 2 more here. We have nitrogen dioxide. So what's the first step in determining what the oxidation state is? Oxidation states are. Whichever one's higher up on our hierarchy list. So that's going to be oxygen, because nitrogen is in 5A. So we use the oxidation state of oxygen to figure out what the oxidation state of nitrogen is. So we'll do the same thing where I do 2 times that -2. So the oxidation state of nitrogen is +4. Yeah, +4. And then we move over to our last one. So we have water, H2O. And now hydrogen is higher up on the hierarchy list. So we start with 2 times that +1 of hydrogen. So the oxidation state of oxygen here is 2 times 1, though. Yeah. So just -2. So in this case, And in some cases, even though hydrogen's higher up on the hierarchy, it doesn't actually change oxygen's oxidation state that it normally forms. All right, so looking at our whole reaction here now, what elements, what atoms have oxidation states that change going from reactants to products? So which oxidation states change going from reactants to products? Tin is one of them. So then tin, it goes from 0 to +4. Yes, and nitrogen, which goes from a +5 to a +4. So which one is being?
So the nitrogen is being reduced and tin is being oxidized?
Yes. Tin goes from 0 to +4, which, right at this number line again. Actually, got to go to 4. So +1, +2, +3, +4. Right, so tin goes from 0 to +4. So that's being, or that oxidation state is increasing. So it's being oxidized. And then for, I guess I can't do that in yellow. For nitrogen, I should have gone to +5. Nitrogen is coming from +5 down to +4. So it's moving to the left on that number line. So that's being reduced. Oops. So this one is, this is tin. Yeah, so tin's being oxidized, nitrogen's being reduced, and then everything else, oxidation states don't change. So the hard thing about balancing redox reactions is that only some of the oxidation states change, and so you have to do this whole thing with the oxidation states, and then you have to figure out how do I balance those electrons. Man, this chapter always goes slow. Okay, any questions? Identifying oxidation states. This is why I added problems. Some of those added problems are just identify the oxidation states for individual elements or ions, and then compounds. Right, it's more of exactly this. So redox reactions occurring in aqueous solutions are difficult to balance by inspection. So that's what we've done for our other chemical reactions, right? You can look at the number of tin or aluminum or nitrates or whatever and just balance the number of atoms and you're good to go. None of the oxidation states there are changing. Because it's electrons that are sort of like changing hands and moving around, right? I mean, before we marked this up, there are no charges indicated for everything. Everything's neutral, so how do you tell, aside from assigning oxidation states, what changes? And even once you've assigned those oxidation states, right, it's kind of hard to balance. The easier way, and the one that's more methodical, which I think is preferred, is to do this half reaction method. So basically you have to identify what's being oxidized and what's being reduced, and then you make those two separate reactions, balance those individually according to some rules, and then you put them back together at the end to get an overall balanced chemical reaction. All right, so for this one, starting off simply enough, we have aluminum reacting with silver. So which of these is being oxidized? Aluminum. So it's being oxidized and silver is being reduced. So when we split these into half reactions, we'll start by taking the aluminum, and its half reaction is going to be aluminum turning into aluminum 3+. And then for silver, it's just the Ag+, which is aqueous, to Ag solid. So those are our two half reactions. So it can get a little bit more complicated, and actually, yeah, let's briefly go back up to this one. So if we wanted to break apart the half reactions in this problem, which is already balanced, we would take the tin and the tin oxide, that would be one half reaction. We take the nitric acid and the nitrogen dioxide, that would be the other half reaction. And then the waters, they get added in as a part of the balancing, which is part of what makes these so hard to balance, is you'll end up adding things in for aqueous reactions. Okay, so we got our aluminum to Al3+, Ag+ to Ag. So these are our half reactions. And then we want to balance each half reaction with respect to mass and charge. And so this is where we're going to start adding things in, and those are going to be electrons. We'll also add in other things to account for mass. But in this case, we have one aluminum atom one in the reactants, one in the products, and then one silver atom in the reactants and one in the products. So we don't need to balance anything with respect to mass. But the charges aren't balanced, because here, for the oxidation half reaction, aluminum has 0 charge, Al3+ has a 3+ charge. And we need that charge to be the same on both sides. So we can add in electrons, which are plus, or E, which you're going to need more than that, E minus. And how many electrons do we need to make it balanced? Yeah, 3. Right? Cancel out all of those positive charges. It gets a little bit trickier because the only thing we can do is add negative charges. We can't add positive charges. So if one side is more negative than the other, then we can only make them equally negative on both sides.
So where are these electrons coming from? Do we just have electrons in our pocket? Or just...
So these electrons are coming from the other half of the reaction.
Okay.
Yeah.
I don't know.
Yes.
Do I
We're.
have electrons? 'Cause I don't.
Wish I did. That'd be kind of cool. Just lightning in a bag.
I don't want your face change. You're like,
Be cool. No, so yeah, because we're taking this reaction, it's a great question actually, because we're not generating things out of nothing, right? We've talked about you can't do that. So you got to remember these reactions are taking place. We're just talking about aqueous redox reactions. So they're taking place in water, and we've split this reaction in half also. So on this one side, it's going to be oxidation is lost. It loses those electrons, but where are they going? They're going to the other half of the reaction. So by breaking this in half, we can count those electrons very easily and visibly like this, and then we'll actually cancel them out from the reactions when we combine them back together.
okay. I was like, this makes sense, but where is it
Yeah,
coming from?
right, yeah. They're coming and going to and from the other reaction. So for our reduction reaction, how many electrons do we need to add, and to which side?
So we need to add up onto the positive side to
Mm-hmm.
balance it out.
Yeah, so you need to look first at which side is more positive, right? So this side has a +1, this side is 0. So we'll add this very conspicuous space here, 1 electron. That'll balance it. Let's forget about the order here. Okay, yeah, so in order for these to actually sort of link up in the end, and for our assumption that aluminum, well, not really assumption, right? We can see here that aluminum loses 3 electrons, but that means that silver has to gain more electrons than we have written out here in just its half reaction. So we can take this entire reaction and multiply it by the number of electrons that we need. Or multiply it, in some cases, by the least common multiple, smallest common multiple, so they have the same number of electrons. So going from this slide to the next slide, you're going to see that we go from 1 silver, 1 electron, 1 silver neutral to 3, 3, and 3. All right, so we multiplied all of the coefficients by 3. So now we have 3 electrons here and 3 electrons there. So we've accounted for the exchange of electrons between these half reactions. So when we add these together, everything we have, just like for ionic, doing complete to net ionic equations, right? We cancel out all of the stuff that remains the same on both sides. That's what we're doing here when we add these together. So this is going to be 3 Ag plus Al, always forget these, aqueous, and then Al3 plus 3 solid. So now we've correctly accounted for that exchange of electrons. So your final check would be to look at the charge on both sides. Say this side has a 3 plus charge. This side also has a 3 plus charge. So reactant products are balanced with respect to charge. Cool. So, procedure for balancing redox reactions using the half reaction method. And this is one, because I did add also to chapter 17, of course, there's problems where you have to balance redox reactions. As you're going through the steps, write the steps next to them so that you remember them. Scam likely. Apparently. Somewhere. I've been getting a lot of scam calls recently. So yeah, as you're going through these, right, you write out your chemical reaction, and then you assign oxidation states. Write 1, assign oxidation states to the side of that, and just keep track of those steps so that you, burn it into your mind. Then you separate the overall reaction into 2 half reactions, one for the reduction, one for the oxidation. Then you balance all elements other than hydrogen and oxygen. This is where it's like, oh, again, where are we getting these hydrogens and oxygens from? Because next we balance it by adding water and then H+. And again, these are all reactions taking place aqueously, so there's excess water around. So it's not coming from nowhere, it's just part of the solution, and it's maybe actually taking place or actually participating in our reaction now. So balance everything except hydrogen and oxygen. Then you balance oxygen by adding H2O. So if you need more oxygen on one side, add the number of waters that you need. Then on the other side, you'll probably have to add hydrogens to balance out all the hydrogens you just added with the water. And we're not going to do basic solutions, but after you've gotten past this point, if you have a basic solution, which would just be told to you in the reaction problem, so if you want to practice those in the examples in the textbook, you can do that. You just neutralize the H plus by adding OH minus. You just add the same number of OH minus to both sides. So the H pluses plus OH minus make H2O. Then you cancel out the number of waters. So after you've added those, you balanced everything with respect to mass. Then you balance each half reaction with respect to charge by adding electrons to the side that needs to become more negative, because we can't make anything more positive. Then you multiply the number, or make the number of electrons in both half reactions equal by multiplying. Sometimes you're going to end up in a situation where you've got 2 electrons in one and 3 in the other. And you got to multiply by 3 and 2 to get those to both be 6. It's a trick we've seen a few times. And then you add the reactions together, cancel out everything that's the same on both sides, and verify that you've both balanced it and that the charges are equal. So redox reactions are the most methodical way, or the half reactions are the most methodical way to do this. Get through at least a couple examples. So balance a redox reaction occurring in acidic aqueous conditions. All right, so what is the first step?
We'll figure out the oxidation state.
Yeah. Identify oxidation states. So, what is the oxidation state of H+? 1+. Cr, chromium solid? 0. Hydrogen. It's an element here by itself. So yeah, and then hydrogen also falls into the weird category of the Brinkelhoff elements that are all diatomic. So in its elemental state, it's H2. So it's 0 oxidation state. And then chromium, 3+, with a 3, or +3, let's do that backwards. +3 oxidation state. So what's being oxidized and what's being reduced? So we're going to split these into half reactions based on which one's being oxidized, which one's being reduced. So chromium, yeah, it goes from 0 to +3. So it's increasing oxidation state. So it's being oxidized. So then Cr solid goes to Cr3+ aqueous. Bless you. And then our other half reaction is what's being reduced, which is oxygen, or hydrogen, not oxygen. So it's going to be H+, not plus, aqueous goes to H2, gas. So those are 2 half reactions. I'm going to start switching up the colors. Okay, so the first thing we need to do is balance these with respect to mass. Balance mass. So, right, the number of atoms have to be the same. And for our first one, we have 1 chromium atom to 1 chromium atom, so that's good. Don't have to balance anything there. For the second one, we have H+ and H2. So the only way we can add anything to these, aside from hydrogen, or what am I trying to say? I guess, yeah, here that kind of combines those 2 steps. So we know that we need 2 H+ to be H2 on the other side. We could also add oxygens if we need to add oxygens by adding water, or hydrogens by adding more H+, if it wasn't already part of the reaction. So that's kind of what we're doing there. And now we need to balance. Well, what do we need to balance next? Yeah, electrons, charge. I'm going to put balance charge. And so we're going to add electrons. So where do we need electrons? Chromium, which side? Well, if I add electrons to the left side, because remember, and this is the confusing part, is we're adding negative charges. So we can only decrease the charge on one side or the other. Yeah.
So you would add it to the right side as well?
Yeah, so we have to add it to the right side. And we're going to add 3 electrons, because that's 3 negative charges. So you can think of, for every electron you're adding, you're subtracting 1. Yes, it is, no, it is confusing. And it was always confusing for me too. I just had to think about it twice.
Yeah.
Yeah. And what about for the hydrogen reaction? How many? How many hydrogens with positive charges do we have? So we have 2 H plus here, so now we have to add 2 electrons. But you're right, we do have to add those to the left side. So now we're balanced with respect to charge. So once we've got mass balanced, charge balanced, now we look at the reactions together, and we have to get the same number of electrons on either side. So I guess balance, electrons between reactions. So for this one, this is another case of the least common multiple. So if we have 3 electrons here and 2 electrons here, hopefully you're beginning to pick up on this pattern, that whenever we have 3 and 2 of something and we need them to be balanced, we're going to multiply them by the other one, because we're going to end up with 6 electrons in each. So we multiply this top one by 2, multiply the bottom one by 3, because 6 is the least common multiple of 2 and 3. So then I'm going to rewrite these. This will be 2 Cr solid goes to 2 Cr3 plus aqueous plus 6 electrons. And then this is going to be 6 H plus 6 electrons and 3 H2 gas. So we're multiplying the coefficients all by either 2 or 3, depending on the reaction. Let's see, I think this color works. Huh. The 6 is only slightly different from that blue. The 6 is like a very bright pink on my screen. So 6, the last step is to combine the 2 reactions together. So take our half reactions and combine them together, because now we have the same number of electrons on either side. So this means that we're saying that 6 electrons came out of the chromium, and those 6 electrons were picked up by the hydrogen to make the 3H2. So this is going to be, and we're going to, right, these electrons will cancel out. This will be 2 Cr solid plus 6 H plus aqueous. Let's do 3 H2 gas plus 2 Cr3 plus aqueous. And then the very last thing is always check to make sure it's actually balanced. So we have 2 chromiums. We got 6 hydrogens on either side. And then the charges are also balanced. So 2 times the 3 plus charge, that gives us 6 plus. And then 6 times the 1 plus charge is also 6 plus. This would be your final answer. So I kind of take up a lot of space But, oh wow, it's 9:48.